Okay, so my plan today is actually we move to the next section. We move to 4.4. Okay. Uh, okay. Let me. Okay, so what we have uh, studied for the past few weeks is we study 4.1, 4.2, 4.3. This is the max mean value. This is the mean value theorem. This is the f prime and f double prime meaning in graph. And we already have 4.5 actually, 4.5. This is the curve sketching. So last week we did some curve sketching, and I also make an additional video for you to check. Okay? So you can check the video and also check the practice that I gave you. Uh, if you have any specific problem within the curve sketching, please let me know, and we can maybe have another maybe one or two example in class. Or if not, I will make another video for you, okay, for specific questions. So this is what we have done for chapter 4. So this is chapter 4. Okay? And my plan today is actually go for 4.4. This is the L'Hopital rule. Okay. Okay, I think you know L'Hopital rule, right, from high school. So I will let you go to why we need to have the L'Hopital rule and how do we know that we can use the L'Hopital rule or not. Okay. Uh, 4.6 we skip. Okay, we skip. This is the same curve sketching, but with the uh, graph calculator, but we just skip that. And then 4.7, this is the we call the optimization. And 4.8 is Newton's method. I think I already talked a little bit Newton's method, but I will let you go to in details of what Newton's method are. And then 4.9 is, we call this is antiderivative. Or we know the terms is, we usually use the integral, but it's not really that the same. There is some difference between antiderivative and an integral. Okay, but in general they are the same, but there is a specific difference between those two. So I hope I can finish 4.4, at least general introduction today, and maybe some example. And next Thursday, also continue a little bit of L'Hopital rule, and maybe take into the 4.7 optimization. Okay. And next week, maybe optimization a little bit, because optimization is, I think, similar with the related rates. If you remember in chapter 3, okay, in chapter 3, there is a related rates. I think it's 3.8. Okay? So related rates, when you have like, remember the triangle, the ladder, okay? And then it's going down for dy dt, and you know that this is dx dt, and asking dy dt, so the dy dt is a, and you have a ladder with fixed length. What is dx over dt? This is a related rates problem. Optimization is pretty much similar, but the idea for optimization is we need to find how to maximize or minimize a functions from real life situation. Okay, for example, you want to maximize making a volumetric like a cube like this, but you only have maybe the paper is x and then maybe how much paper you have and how to optimize to make how much the cube you can make, that kind of problem. Okay, that kind of problem. Okay, so I think the optimizations uh, you have learned before in a simple way. Maybe back in elementary school you have learned optimization, but now we are with some more a little bit complicated, and we solve with calculus. So we find the max or the mean value to find for some problems. So basically similar. So you will be given long words that I think you don't like, right? Right? You don't like long words, and sometimes it's difficult to understand, right? So I hopefully within these chapters I can give you some tips on how to solve the problems. Okay. So that's optimization. So okay, let's start with the feedback. Okay, the feedback from last week. Okay, I think this is the questions, right? Okay. So okay, okay. Let's read the question. Consider the graph f prime or f first derivative of f. Okay. On what intervals, okay, is f decreasing? Okay. Okay. So first thing, remember, if you have f prime pass, then f prime, it can be positive, it can be negative. Okay. Positive means it's increasing. So the function is increasing. If negative, the function is decreasing. Okay. This is the principle, the first thing you need to think first. Okay. And also it can be also f prime is equal 0, meaning this will be the critical. It may be a critical point, right? Critical point. Okay, so let's look at this graph. Okay, this is f prime. Okay, the blue one is f prime. So within the this is positive, right? This is negative. Okay, got it? So how to find the decreasing one? Decreasing one is if you have f prime is less than 0, right? The graph is f prime. It's the first derivative. The graph is f derivative. Okay. So if this is derivative, then we need to just to find y-axis that is negative, right? So the one that negative is this one and this one, right? So that will be the answer. Okay. So 0 to 1, and this is 3, 4, 5, 6, 7. Okay, so 7 and 8. Okay. So that will be number the option, the first option here. Okay. I think you did a good job here. Okay. 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 Next questions. Oh, maybe any questions here? I think it's quite okay, right? Okay. Next question is okay. Now this is a little bit uh, a tricky statement. Okay. So f prime is 0, and then the statement say that f has local max or minimum, right? Remember, if we have this, okay, let me just draw this really quick. Okay, this is a local max, right? We can say this is a local max, okay, or just max in general, right? But at this point, is this true? No, right? We say that f prime is undefined. So for a function to have a local max or minimum, it doesn't need to be f prime equals 0. But f prime equals 0, for sure, it must be a critical point. For example, if you have a graph like x cubed like this, the point in the middle here, probably this will be f prime equals 0. But of course, we don't know that if they are minimum or maximum. But we know for sure this is f prime 0. Okay, but not necessary to be max or min. Okay, I hope from that explanation it gave you an idea. Okay, so f prime will be having a critical point, but we are still not sure whether it is a local max or local min. We need to check with other tests. Okay, we can check with the concavity. We can check with the check the endpoint if the function has interval. Okay. Okay. So it should be false. Okay, it should be false. So this is false. Okay. Now okay. So I hope you understand the question. Okay. So for what values of the constants a and b, okay, from the function here, the y equal ax cubed plus bx squared is 1 and 3 a point of inflection. So this is inflection point. Okay. Okay. Now remember, inflection point happening on if your double prime or second derivative is equal 0. Okay. So first, maybe we can derive twice. Derive this become okay. And maybe second time. Let me check. Change the color. Okay, Jonathan. I'll show you that later. Okay. Okay, and it should be equal 0. And then we know that our inflection point happening at x. So maybe we can take this inflection point at x equal 1. So we know that 6a plus 2b is equal 0. Okay. And then perhaps we can check the original one when let's say fx is ax cubed plus bx squared. Check the x equal 1. A plus b, this is equal 3. And I think we can check this. And maybe we can take maybe multiply with 2. And then minus 6 minus 2 for A is 3. And B to B is negative 6A. Okay, I think I make a mistake. Did you know where I make a mistake? So point of inflection, A plus B is 3, 6A, 6A plus 2, 2B 0. Three and B. A plus B. 2b x 6a. Let me check the questions. Oh, meanwhile, if you come late, you can check the QR code again. Okay, so Jonathan, if you want to check the QR code. Okay, wait a minute. Okay, let's. Okay. Sorry. Okay, wait a minute. Oh, I think I make a mistake here. Okay. Sorry. Let me just erase first. Okay. Okay, should be. Okay, should be. First, checking the F1. This will be a plus b equal 3. This is the first equation. Okay, oh yeah, this is what I did wrong. Okay. Okay, sorry. So 6ax plus 2b is 0. Then 6ax, we solve this first. Okay. We solve this first, and then we make this x is equal 1. So 1 is equal 3a. Okay. Okay, now, okay. I why make that mistake? Okay, and then put here. So minus b is 3a, or b is negative 3a. A minus 3a is 3. So this will be 3. So a is negative 3 over 2. Okay. So b will be 3 plus 3 over 2. Or we can say that this will be b 9 over 2. Okay. Or actually, if you have the time, we can check through the y. We can check and then find the second derivative, make it 0, find the x, and if we can find that x equal 1, then the answer will be true. Okay? If you want, we can check. It is 9 over 2 squared plus 9x, and then we can second derivative. It will be negative 9x plus 9. This will be 0, or this will be x plus x minus 1. So we get x is equal 1. Yeah, we can check. Okay. And eventually, okay, another way to look at the functions. Actually, from these options, if you have the time, you can check one by one. You can check one by one if the time enough. Okay, if time enough. But of course, if it's in exam, um, if you're doing this, like checking one by one, maybe not a full point. Okay, not a full point, but it can still be done. Okay. Okay. Yeah, actually, I did the right thing before. I messed up here. Yeah, sorry. Okay. Let me check the sections. Okay. Okay. To begin with, the new section. This is 4.4. This is include the L'Hopital rule and the indeterminate form. Okay, the title, L'Hopital rule. The L'Hopital rule is the name of the technique. Okay, the technique. The indeterminate form is the limit form that you can do. Okay, for example, I will give the simple version first. Okay, for example, you have limit x 0. This is f divided by g. Okay, if limit if this is 0 and this is also 0, okay, this will be 0 over 0, right? 0 over 0. Okay, we call this form 0 over 0. This is indeterminate. Okay, we call this indeterminate form. Okay, so we are not sure what is that form. Okay, whether it is because 0 divided by a number is 0, but something divided by 0 is an infinite. So we are not sure whether it's going to be infinite or it will be going to be 0. Which one is faster, 0 or infinity? We are not sure. So that's why we cannot determine. So it's called the indeterminate form. We cannot determine whether it's 0 or infinity. Okay, and there will be other form still we call indeterminate. So the first form is 0 over 0. Okay. Now, The L'Hopital rules say that if we find this 0 over 0, what we can do is we are going to, we can maybe, so we can, usually you're writing LH like that to show that it is using L'Hopital rule. So LH means the L'Hopital process. Okay? So this will become the derivative of the each function. Okay. So this is a simple way to look at. Okay. Let me give you this first. Okay? And I will give you why this is the first derivative. Okay. So in practice or in maybe solving problems, when you find limit, you see 0 over 0 situation. What you can do is you can do L'Hopital. You can derive the top equation and derive bottom equation. If it's still 0 over 0, you can do as many as you want. Maybe 2, 3 times until you get something that when you put in the limit, it has the number or it has the result. Okay. So you can L'Hopital, L'Hopital, L'Hopital many times. You can many times. Okay. As long as it's still 0 over 0, you can do as many as you want. Okay. Okay. Now, on why we are going to look at why this is true. Okay. Okay, let me go through. Okay. Let me go through some example. Okay. Let me write a function. Okay. Just a quadratic easy functions that you can also draw. Right. Easy to draw. Right. X squared plus 3x minus 4. And let me draw another function that I think you already also know how to draw. Is the ln. Okay. The first one, the functions will be like this, right? Just the regular quadratic, okay, x squared, okay? And ln x will be something like that, right? It goes down when it's closer to 0, right? Okay. Let me draw these two curve, okay? Roughly, I'm trying to draw these two. Okay, the first one we can factorize, right? We can factorize. Okay, we can factorize, and we know the roots is -4 and 1. So we may have maybe one is here and -4 here. And maybe if you look at the extreme point, it will be around -3 over 2. Okay, so we will have this. Yeah, if you want to take some value, but I believe the value will be a negative around -3 over 2 will be here, maybe around here. So maybe around that point. Okay, let me just draw. Okay. Okay, for example, this is our drawing. Okay. Now the other one, the ln. Remember the ln at 1 is 0, so practically it's crossing 1, right? And then it's at 0, so it will be maybe, okay, maybe like that. Okay, maybe around. Okay, so this is ln x or gx, okay? And this will be fx. Okay, now if I give you the limit as x approaching 1, okay, fx divided by gx. Okay, now to imagine what this question about, okay, Remember, limit as x approaching 1. So, oh, let me draw 1 here. Okay, let me draw 1. So 1 is here. Okay. So we can imagine we approach 1 from the left, and we approach 1 from the right. Okay. Now I draw separately f and g. Okay. Now we can see and observe f and g separately. If we look at this point here, near closer to 1, maybe let me make some make a circle. Okay, let me make some circle. Okay. If I zoom in to this point here from this circle, going closer, and you see, use your imaginations. Okay, this too is a curve. Okay, like for example, the G is having a curve like that. The F is also having a curve like that. But when you zoom in, this line here becomes like a linear. Okay? And even you can see from here, because of the pixels, there is some limitations that you can see just, okay, this is just like a line, like a slope, the slope of the curve. Okay, so let me mark the slope. Okay, let me mark the slope. So maybe this is the slope for the green one, and maybe this is another for the F. Okay, now if we break, the slope becomes the component y and x. Okay, this will have, this is dg. Okay, or let me make some pointer. This is dg, and the x one is dx. Okay, and the other one, this will be df, and this is dx. Okay, now if you see the proportions of dg over dx, that will be the slope. Okay, you see the proportion of df over dx, that will be the slope. And if we are going to look at the ratio or the proportions, okay, if we take the ratio of f of x divided by g of x, we are going to see the proportions of, so imagine, okay, so when we zoom in, it will be similar with the slope, right? Similar with the slope. So we can make sure that the ratio of f over g, we can take the ratio of, this is df over dx, and then this is dg over dx. Okay, and that's why this is actually f prime g prime. But of course, this is happening only when x is near 1. Okay, okay. So at the closer x, okay, if you look the graph, if you look the graph, the curve will be like its slope, the same as its slope, and this is also the same as its slope. So when we have f over g and it's going closer to 1 point here, okay, it will be having the same proportion. Okay, and that's why we have the f over g is the same proportions of its slope. Okay, okay, that's from some of our observations. Okay, from the graph. If you want to be maybe more uh, clear in the graph, you can check the graph using the graphing calculator and zoom in the area where the point is going to meet at this one, right? Because when you see this one here, it's going to have a zero value, right? It's going to have a zero value. Okay. Okay, if you look at the uh, the point here, when you have 1, this is 0. When you have also 1, this is also 0. So both are going to have 0 results. But when you have in this f over g, this will be a 0 over 0. So what will happen? We did another approach that we have talked previously. That is, we are going to see that this is actually the slope. Okay? That the curve is actually the slope. So we can approach with the slope. Okay. So this is the first. We call this the visually or intuitions definition for the L'Hopital rule. Okay. Okay, that's the the introductions for L'Hopital. Okay. Okay, if we want to look more in a little bit details, okay. If you look here, okay, there are two graphs, okay, that I already mentioned before. If you look f and g, just a random function, but they have intersections here. They cross at a0. Okay, they cross at a0. So meaning at x equal a, both of f and g will be 0, right? Here. Yeah. And if you look at what will happen with their slope, okay, if we look at the slope, okay, so the red curve becomes this slope with m1 as the gradient, and the blue slope becomes this m2 with gradient m2. It seems that the proportions, like I said before, it seems that when we are having closer to a here, it's the same as the slope. Okay, it's the same as the slope. Okay. Okay. Now, how to uh, how to make some a simple proof that this is actually going to be true. Okay. Okay. Let me give you some notes for that. So L'Hopital rule. First, okay, let f of x and g of x, they are both differentiable and continuous. At x equal a, fa is equal ga is equal 0. And the third one, the first derivative of g should not be equal 0. Okay, from these three statements, let me just make a simple proof, okay, for you. Okay, I think that's enough just for this statement. The actual proof is a lot more than this statement, but let me just give you this simple proof. Okay, so limit as x approaching a of f of x divided by g of x. This simply we can do L'Hopital here. Okay. Now to prove this, let me start with this. Let me write one more time. Okay, to start with, let me subtract this two. Okay. Subtract with zero. Subtract with zero. It's just zero, right? But zero, by our definition of f of a and g of a, this will be zero as well, right? So we can take this in terms of f of a and g of a, okay? Because both are zero, okay? And then we are going to multiply with 1 over x minus a, 1 over x minus a. So our limit becomes f of x minus f of a divided x minus a, and this is g of x minus g of a, and x minus a. And this is derivative definition, okay? The derivative by limit definition. Okay, right? This is or we can say directly. Okay. So, okay, if you have okay limit x equal 1 approach 1, let's just start with this example. If this happen, then this will be we can make sure that we check first. Okay, check first. Make sure this is 0 over 0. Okay, and then if it is 0 over 0, then we can take the L'Hopital rule, and this will be, don't forget the limit. We still have the limit, and 1 over x, and then this is 1, so this will 1 over x. Substitute 1, it's become 1. Okay. And if you if it has another example, I just give a simple example first. Okay. Later I will give you a little bit complicated one. So if this is e to the x and then over x squared, okay, what will happen now? Now we have not 0 over 0, but this will have infinite over infinite. Okay. But why L'Hopital rule still applicable here? If you remember, okay, if you remember, when we have limit, and then we have the, for example, 1 over x, this is x going to have approaching infinity. this will be, in limit, this is 0, right? So actually, the same thing for infinity divided infinity. The same property will also applicable for us to use the L'Hopital rule. Okay, so 0/0, we can use L'Hopital, and infinite, we can also use L'Hopital, because we remember that in limit, when we have x approaching infinite for 1/x, this will result 0. So actually, if we have infinite, this is how to say, a similar property with 0/0. Okay, so we can take this into a L'Hopital process. So this is the first derivative, it's just e to the x, same form. The bottom one is 2x. Still infinite over infinite. Take one more step. L'Hopital one more. And this will be resulting infinite. Okay. Okay, any questions first? Any questions first? Okay. Okay, this is just a review of what we done. Okay. So the basis for the L'Hopital rule is, if the limit of f is 0, limit of g is 0, okay, and also if limit of f is infinite or negative infinity, same way g is positive or negative infinity, then okay, we can apply the L'Hopital rule, which means if you see any 0/0 or infinite over infinite or negative infinity, or uh, yeah, or yeah, 0/0 or negative infinite over infinite, then we can apply L'Hopital rule. We can derive the top equations and the bottom equations. Okay. Okay. Of course, we need to prove that the limit exists. Okay. Okay. Let me take to another example that uh, probably, or maybe in another slide. I think I can make this bigger. Okay. Yeah, this is just mentioning what we have done previously. Okay. Okay, let me go new page. Okay. Okay, another example. Okay, first we check. Okay, first we check ln and then square root. Okay, still it seems that it's infinite over infinite. Okay, then let's apply the L'Hopital rule. This will be 1/x. Okay, this will be 1/. Okay. Now this is, I think, important notes for you. Okay, if you check directly infinity to here and here, okay, it will be 1 over infinite, right? And it will be 0, right? And maybe on your mind, okay, let me do L'Hopital rule one more time. But this is actually, you shouldn't do that first, okay? What you need to do is, you need to rewrite form and whether this x can cancel this, right? Okay, so that you should do first. Okay? So instead of doing L'Hopital one more from this point here, what you can do is rewrite the form, simplify the form, and simplify the form. Or this will cancel this, and this will be okay. And now we are going to see that if we plug in infinite here, it will be a 0, right? 2 over infinite, that will be 0. Okay. 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 So before doing the L'Hopital, look at the form first. Sometimes you need to rewrite the form, okay? And maybe you need to cancel out some terms, okay? Okay. Another example. Okay. Tangent x minus x over x cubed. Okay. Now, if you have this, first thing, every time you see a limit, check the x value. Okay? Check. Always check. Okay. Check the x value, and it is 0 and 0, so 0 over 0 situations. Indeterminate forms, then we can apply the L'Hopital rule. And if you look here, it's still 0 over 0 again, right? Secant 0 is 1, so 1 minus 1 is 0, so 0 over 0. We can do L'Hopital rule again. So secant squared, okay, 2 secant x, and then secant x tangent x, right? So you have secant squared x tangent x. This is 6x like that. Okay, and then what's happened? So this will be 1 over 3. Or let me move this going here, this going here. Okay. Okay. So secant x, and then tangent x over x, and this will be secant squared x. Or I can make this to be separated and make it limit x. Okay. This one is 1. And limit x approaching 0, tangent x over x is also 1, right? Okay. This is because I hope you still remember, okay, that the definition on sine, if you have limit of sine, this is 1. Okay. Okay. because tangent is sine over cos, right? Okay. So we can write this as 1 over 3. But instead of doing that, if you look the secant squared here, we can also write identity formula for trigonometry. So we can exchange the secant squared with tangent squared plus 1. Okay. So what will happen here, let me use different color. Let me use dark blue. This will be tangent squared x plus 1 minus 1. And this will divide 3x squared. Okay. So this will be canceled. And I can write this terms. Let me factorize 1 over 3 and limit. This becomes tangent x over x. Also limit tangent x over x. So this is 1, this is 1 also. So again, it's the same 1 over 3. Okay. Which method you prefer, it's up to you. If you want to rewrite the form, exchange the secant squared with tangent squared plus 1, that's also okay. Or you want to take another L'Hopital, that's also okay. That's also okay. So both are okay. Okay. Both methods are okay. Okay. Again, in calculus, not all problem can be solved directly with calculus. Sometimes you need to use some algebra, rewrite the form. Okay, like this one. This is some algebra here, and this L'Hopital is directly calculus. Okay, so it's calculus, calculus, calculus. Like you have the, remember you have the log, right? You have the log. Instead of directly derive the log, you can maybe separate the log, or like for example, you have the ln, in terms of f of x and then g of x here. Okay. Instead directly find the derivative, you can maybe make this first separate becomes 2 ln like that, and then each one of them we can derive easily. Okay. Instead just like this, and then you derive, and then you probably mix in your head with fx, you need to product rule, right? Okay. Or even if this is fx over gx, you need to have a quotient rule, right? It's best if you separate. Okay. Like for example, this one, I think both methods here not really that different. I mean, uh, the difficulty is similar. If you go here and go here, if you compare, it's probably a little bit similar. Not really that difficult. Okay. 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 Now, okay, if you have limit x approaching from the right to 0, x ln x. Okay. Why this I have from right here? Because ln x is only on the right side. It's just to have uh, a good approximation on how ln will be. So if you have ln, if you have 0 here, ln will be going down, right? Ln will be going down. Like this, the ln, right? And then it multiplies with x. So if you see the limit, x is approaching 0. So this 0 and this will be approaching infinite. But which one is faster? Is it 0 or infinite? So this will be, again, another interesting question. So this will be 0 multiplied with infinity, right? And it's not something that we can solve. It's also indeterminate. Okay, it's also indeterminate. We call this indeterminate products. Okay, indeterminate products. Okay, let me give you before I solve the left one. Let me give you something to think. Okay, so let's say we have limit. Okay, this will be 0, right? And limit, this will be infinity. If we have limit of x squared multiplied by 1 over x. Of course, because of the terms of x squared and x, we know that it will be a 0, okay? Right? If we have limit, this is 0. If we have limit 1 over x squared, this will be infinite. Same way, if we look at the products from these two, it's 1 over x. It's 1 over 0, so it will be infinity. Okay. This is a few example on what case that might be. Okay. For this example, another case that might happen is if limit this is just 1 over x. This is infinite, but when you multiply, this is just 1, just a finite result. So, okay, from this product here, 0 infinite, actually what might happen is you can get 0, you can get infinite, you can get 1. It depends on the functions and the case conditions, right? But of course, we need to make some solutions, some general solutions through the L'Hopital rule if we want. Okay? We can think the f multiplied with g. Okay? We can think this as f and then 1 over g. Or, okay, or this is g 1 over f. Okay. So the idea, okay, we going back to 0 over 0 or infinite over infinite. Okay. So if you look here, x ln x. Okay. We can take ln x divided by 1 over x or x and 1 over ln x. Okay. One way is better than the other way because of the results. Okay. So let's check. So we can check this and make it ln x divided by 1 over x. So if we're doing this, this seems infinite over infinite, and seems that we can make our L'Hopital process. Okay, so we can make L'Hopital process. Take this L'Hopital, and we can have 1 over x, and then negative 1 over x squared. So we will have limit. This will be negative x, so it should be 0. So in this case, it will be going to have 0. Okay. So 0 is faster than the infinity. Okay. If we have the x ln x, so it makes the answer going to be 0 based on our L'Hopital rule. Okay. But if you check x divided by 1 over ln x, if you check the L'Hopital, it will be difficult because 1 over ln x, there will be some complicated form And yeah, I'm not suggesting that. Okay. Okay. So indeterminate forms, 0 over 0, infinite over infinite, and then indeterminate products, 0 multiplied with infinite, it's also indeterminate, which you can also solve by L'Hopital rule. Okay. The other one, there are two more. Okay, two more types. If limit this is infinite and limit is also infinite. Okay. What's happened with limit? So you have f and g. Okay. Both limit. If you approach with the same number a, they both having infinite. Okay. Both having infinite. Okay. And then what will happen with this limit? X approaching the same a, but this is f of x minus g of x. So it will be infinite minus infinite, right? And okay, again, uh, don't write this, okay? This is wrong, okay? Because we are not sure whether this becomes positive infinity in the terms or it becomes negative infinity because this part is maybe bigger, but infinity is already an abstract value. But we know that if we have infinite, then there will be something really big that we cannot calculate, right? And also maybe it will be some finite results. Okay, so how do we do? Okay, so this is also indeterminate forms. It's called the this is called the indeterminate difference. Okay, let me give you an example on how to solve this type of limit. Okay, if you look here, okay, if you look here, both 1 over ln x, it will be making 1 over 0, which is infinite. This will also 1 over 0, which means it's infinite. So it's infinite minus infinite. It's indeterminate difference. How do you solve this? We make a common denominator, which means we can conjugate both functions. So we can rewrite the form. Okay, and when we see the form, we know that okay, this is still uh, 0 over 0, right? It's 0 over 0. Then we can do L'Hopital rule. Okay. So the idea, okay, the idea from the first type, second type, the third type, is the same. We need to make 0 over 0. Okay? We need to make 0 over 0. Okay, we can switch the functions, and for this one, we can conjugate the functions and see whether we can make a 0 over 0 or not. Okay? So if this is 0 over 0, then we can do L'Hopital rule. Okay? So we can do L'Hopital rule. Oh, I need to charge my pencil. So, I think we can write down. Okay, now we can do some L'Hopital. Okay, this one becomes 1 minus 1 over x, okay, from x and ln x. And the bottom one will be, we can use product rule. So we will have 1 over x minus 1 plus ln x, and then 1, okay? If we multiply with x, okay, x over x, this will be x minus 1 divided by x minus 1 plus x and x. I think still it is 0 over 0, so we can do some L'Hopital rule. So L'Hopital rule one more. This is 1 plus, this will be ln x plus x over x, okay? So ln x will be 0. This will be 1. So this will be 1 over 2. Okay. I think for today, I would just show you the form first, and maybe we have more example on next Thursday. Another example that might happen from this difference is something maybe you have if you have this, okay, e with power of x minus x. Okay. Of course, if you look the first example for the indeterminate difference, we can make conjugate because the functions are in a fraction form, right? So let me go through here. Because this is a fraction, then we are thinking, oh, maybe we can make some conjugation, okay? And we make some simplified form. We see the evaluations, it's 0 over 0. Oh, we can make a L'Hopital. We take some calculations. Okay? And then we see that, oh, still 0 over 0. One more time, L'Hopital rule. And then I think we can have some result that is 1 over 2. Okay? So this is indeterminate difference. So infinite minus infinite. Okay? The second example that I show you here, if you look at e to the x minus x, okay? It's just as simple as that. If you check the infinite, it will be infinite minus infinite, right? But there is no fraction here. Now what you can do now? Okay. First, okay, if you want to answer with logics, you can do that. You can imagine the e to the x, the exponential function, because it's increasing really fast. If you draw the graph, it will be increasing really fast. If you compare with the x, of course, it will be going faster. It's much bigger than x, or much increasing in a faster way compared with x. Because of that, we can make sure that this limit will be infinite. We can answer in terms of our logical reason. But if not, we can make some some form. Okay, let's take out x. Okay, so this will be e to the x over x minus 1. So this term, e to the x over x, will go to infinity as x goes to infinity. So we will have a products that will be growing really, really fast. Okay, because this will be going to infinite as x going to infinite. So x is going to infinite. This is faster than this, and you will see that, of course, it will be the difference is way uh, uh, really wide. We can pretty sure that the e to the x over x will be going to have infinity. So we will have the answer that this is will be infinity. So both factors, this grow infinite, this grow infinite. Of course, this will go infinite. How many times left we have? Okay. Okay. Last types of the indeterminate forms. Okay. Last types. So we will have four types: 0 over 0, infinite over infinite, and then the second one is the 0 infinite multiply. The third one is this one, infinite minus infinite. The fourth type is the power. Okay, so it's called the indeterminate powers. Okay, this is if so the function is in the power. Okay, in terms of power. So this will be a 0 with power of 0. Okay, let me write first and then let me explain. This will be infinite with power of 0. And the last one is really interesting, but I think we'll have explanation more in next week. But let me write all first. Okay, this will be 1 over infinite. Okay, we will have three kinds that we are going to group all these three into indeterminate powers. Okay? 0 with power of 0, infinite with power of 0, and 1 with power of infinite. Okay. Okay. Maybe you're thinking, uh, if something has power 0, it should be 1, right? but it's zero. It's zero. Okay. So it's peculiar. And remember, okay, what we are talking here is not the exact number. It's in terms of limit. Okay? It's in terms of limit. So for example, 1 increase with infinite power. If we are not talking about limit, it's 1. Okay? But of course, infinite is the definition is we have in limit, right? So in actual reality, there will be no infinite, right? But we might have, if we have 1 uh, and we have 2 million, this is 1, right? Okay. But because this is in terms of limit, this 1 here is actually not exactly 1. Maybe it's 1 point something, okay? Because it's, remember, it's limit. So this is not the same base, not the same base. This is exactly 1, exactly 1. This is not exactly 1. I will explain this next Thursday, okay? I don't think I have time to explain this, okay? But let me explain how to solve first, okay? If you have questions in this form first, okay? Okay, we call this indeterminate powers. Okay. Now to solve this, example, okay, for example, limit as x approaching 0 from the right of x with power of x. Okay. If we look at the limit, this is 0 with power of 0. Okay. Now how to solve this? First, we can take this x with power of x as some equations. So let's say we have y. Okay, we take the ln of y so that the x can be put down here, right? And after that, we can evaluate the limit. But remember, this is the evaluation of limit of ln. Okay, we already done this before, right? The limit of this from previous one is 0, right? If you if you want to make some precise calculations, this will be ln x divided by 1 over x, and then L'Hopital rule, and they become 1 over x, and become negative x, right? So if we plug in 0, it will be 0. Okay? We already done that. So this ln y is 0, but it's not the final result. It's ln. Okay? So the limit of x with power of x is e with the limit x x ln x, or this will be e with power of 0, 1. So you can make this equation first, y equal x with power of x, and then solve in terms of ln. Take the limit, take the limit, and x ln x is our indeterminate, right? Indeterminate product. This will be 0 and infinite. We take some, change the form, and L'Hopital rule, make it negative x, and put in 0, it's 0, okay? And then we're going to put the, because it's ln, then we need to take that as our power, okay? So e with power, and this is equal 1. Or we can make a direct approach directly. Okay, so you can first find this first, find the ln first, or we can directly write this in terms of okay, we can write directly like this. And remember, in if you have e, and then you have limit, you can write E limit, because you only evaluate the x value, okay? Because E is always having a positive value, right? So limit x approaching 0 of x ln x. And then from here, you know that this is the same as we done before. It's 0, so E with power of 0, this is 1. Okay. Okay. Also, if you notice, okay, we have 0 power 0, and then infinite power 0, and then 1 power infinite. We don't have 0 with power of infinity. Okay? That will be some exception. I will explain next Thursday. Okay. Okay. I think we can have a one or two. I think one example for this one. Okay. Okay. Maybe I'm giving you just one example for this indeterminate power. If you have x with 1 over x. Okay. I think you can check the if y equal x. You can check this and then take the ln, right? And then we can take the limit. If you see the limit here is already ln x divided by x, that is infinite over infinite, in which you can take the L'Hopital rule, okay? And this will be exactly the limit x approach infinite, and it will be 0, okay? So E with the power of limit x approaching infinite 1 over x ln x, this will be resulting E with the power of 0, it's 1. Okay. And I think there are more example. I can make the maybe just give you the some questions, and then you can try to work out on your own. But what I want to do next Thursday is uh, review, just review pretty much the of especially this one, this indeterminate powers, okay, to give you some explanations on this, especially this one with power of infinity and the exceptions. We don't have the so exceptions. So except 0 infinity. So this is an exception that I can show you why on next Thursday. Okay. So far, I think this will be the L'Hopital rule and indeterminate forms. Okay. So now, if you have limit questions, when you have indeterminate, you can solve it through L'Hopital rule. Okay. But remember, L'Hopital rule is not the best way to solve. Sometimes maybe when you derive, maybe it makes things complicated and you need to think another way. Maybe you need to rewrite the form first and then L'Hopital, or maybe no need L'Hopital at all. It depends on you. It depends on you which one you prefer. But this is one method to solve the limit. When you have the limit is 0/0 or infinite over infinite. Okay. Okay. Any questions? Any questions? Okay. Any questions? Okay. I think today's content is okay, right? And any questions about the question on the curve sketching? Something difficult you have? Maybe you try and then maybe you have some difficulty. You can let me know if you want to, like maybe, for example, I gave you several numbers, right? And maybe you can let me know which number that you think it's really difficult. Okay, it's really difficult. Difficult means that if you try and then maybe you can think that, oh, this is actually doable. I think I can do it. I think you can do it, right? But if you think that the question is you still no clue on how to solve it, let me know. Okay, let me know, and maybe I will make another video, or maybe I will show some solution in class. Okay. Okay. So how about the online students? Do you have any questions? Oh yeah, the midterm. Okay, the midterm exam we will have now is 16, so we will have maybe around the end of the November, maybe 30, maybe yeah, 30 November, maybe. Yeah, maybe I will let you know the exact schedule. Okay, but if you have schedule that's really maybe related to other course, or maybe another activity you do, just let me know. Okay, I will arrange the schedule, okay, because our midterm will be flexible. Okay. But for now, the default schedule will be the end of November. At the end of November, the midterm will be physical class. Okay, physical class exam. So you, please come to the class. Okay. Okay. Now I'm preparing the feedback for you. Okay. So let's. If there's no questions, so let me stop this presentation and giving you the. Okay. I just want to know how the today's class uh, can help you to solve some problem in section 4.4. Okay. 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 I think we can start. Okay. Yeah. I think we can start. 3, 2, 1. Okay, let's start. Okay. Sorry if it's too hard. Okay. I'll give enough time, I think. Okay, 20 seconds. Okay. 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 Okay, next question. 3, 2, 1. Okay, just 2 questions for today. Okay. 19. 3, 2, 1. Okay. Okay, I think. Okay. Good, good. A lot of you good, good, good. Correct answer. Okay. Okay, so I need your student ID. Bell, who is Bell? I'm sure it's not your real name. Can I have your student ID? Okay, who's this student? Oh, okay, okay, okay. Okay, I think that's it for today. We'll continue some explanations about the indeterminate powers and some maybe 2 or 3 examples that necessary for you. So yeah, that's the lecture for today.